Hi everyone, first of all, Happy New Year. In today's video I would like to go over all of the new features in the new version of Hugging Face Transformers. So Hugging Face Transformers, if you don't know, is this open source library, so you can find all the code on GitHub, that provides easy access to a lot of state-of-the-art machine learning models, mainly in PyTorch, which is a deep learning framework developed by Facebook, now called Meta. And yeah, actually the Transformers library itself started with a text model, namely BERT. So initially the Transformers library was actually called PyTorch pre-trained BERT because it only included the BERT model from Google, which at the time was really a big breakthrough in natural language processing, or NLP. Because yes, the BERT model was simply getting better results on several benchmarks. For example, the GLUE benchmark, which is quite a well-known benchmark in the world of natural language processing. Of course, nowadays this benchmark is entirely saturated, but at the time the BERT model really got state-of-the-art on this benchmark, which mainly was a text classification benchmark. So for example, classifying the sentiment of a sentence, like for example deciding whether a movie review is positive or negative, and so on. And so when BERT came out, Google open sourced it, so you can find the code for that as well on GitHub, and all the code of that was in TensorFlow. So at the time, this was, as you can see, created 7 years ago. At the time, TensorFlow was really a very popular framework for developing neural networks. However, nowadays, usage of TensorFlow really has dropped a lot, and people have moved on to use PyTorch nowadays. This mainly has to do, I think, with complexity of using models and training models. TensorFlow has basically become so popular and so big that a lot of the features, like an insane amount of features, were added into that framework. As you can see, it's still a very popular framework on GitHub, getting nearly 200,000 stars. But yeah, it became so large and so complex that if you wanted to do simple things, like for example developing a new neural network architecture, it was pretty hard to use or to debug. And so a lot of people then switched to using PyTorch, which you can also find on GitHub. And I really love PyTorch myself as well. And so nowadays, every time a new model comes out and is being integrated into the Transformers library, we typically implement it first in PyTorch. People have the freedom to also add a TensorFlow or JAX implementation. So JAX is yet another framework library for implementing neural networks. JAX is basically NumPy but accelerated on devices like GPUs and TPUs, which is the hardware that Google develops. And then you also have neural network libraries on top of JAX like Flex. We mainly focus on using PyTorch. And so when Google released their BERT model 7 years ago, it was pretty hard to get started with. A lot of people wanted actually to use the BERT model in PyTorch, but that was not available yet. It was only released here in TensorFlow, and also you had to set up quite a bunch of packages to install on your machine just to get started with the BERT model. So then Thomas Wolf, who is actually one of the co-founders of Hugging Face, not this one, but this one indeed, he actually decided to implement this BERT model from scratch in PyTorch, and then basically convert the weights, because the weights were open source here. You can find the pre-trained weights of the various BERT variants here, and then basically convert those weights into a PyTorch model implementation. And in that way, people could actually get started with the state-of-the-art BERT model in just a few lines of code. And this really was the start of the Transformers library. So at the time it was only called PyTorch pre-trained BERT because it was in PyTorch and it only contained the BERT model. Then was later renamed to be called PyTorch Transformers because After BERT came out, actually a lot of new models came out that were all based on the original transformer model, which preceded BERT and which was released in the Attention is All You Need paper by Google in 2017. So, for example, there was GPT-1, which came out from OpenAI. And yeah, at the time, OpenAI was actually open, so they released also the weights of their first GPT model. And so, yeah, people then also started implementing this. I think this was also done by Thomas Wolf. So you can find GPT-1 on Hugging Face as well in the Transformers library. And so as more and more models came out that were all based on the transformer architecture, the library was renamed from PyTorch pre-trained BERT towards PyTorch transformers. And then people actually also wanted to have several models be available in frameworks like TensorFlow. So then the transformers library basically became a framework agnostic library. So then was renamed a third time to be called just transformers. And so it all started with models like BERT and then GPT, but nowadays, as you can see, the Transformers library includes a huge list of not only text models, but actually also other modalities. So if I collapse this section over here, you can see that also a lot of vision models are now available as well. Yeah, for all kinds of computer vision applications, but also audio models for doing things like audio classification, speech recognition, and so on, text-to-speech as well. Video models even, so if you wanted to do video classification, there are models available for that in the Transformers library. And then, of course, multimodal models. So multimodal models are models that combine multiple modalities, like vision and language, for example, in a single model. So actually nowadays, most of the AI models that come out are multimodal. Like, for example, also the closed source models like GPT-4o, for example, from OpenAI is a multimodal model because it can take in both text and images as an input, and it can produce, for example, text as an output. And as you can see, we already include a lot of multimodal models over here as well. And then even some other modalities as well, like reinforcement learning, time series forecasting, and graph neural networks. So yeah, a lot of applications. I think nowadays the Transformers library includes more than 200 different AI models. And I personally also contributed quite a bunch of models to the Transformers library, so you can actually find them all in the source code here. So if you go to the models folder, you will actually find a implementation for each of the 200 models that are available here. And so today I actually want to talk about the latest release of the Transformers library, because there was a new release yesterday, version 4.48. And it's just packed with a lot of stuff. So I just wanted to make this video to go over a bit all of the features, because otherwise it's probably hard for people to just know that some new things are added. And also, yeah, just to explain a bit what the new features are about. So as you can see, yeah, there are a lot of things to unpack here. I think a lot of the new features are simply new AI models that are added to the Transformers library. So yeah, I will just go over all of the new features one by one. So the first one here is that there was a new AI model added to the Transformers library called ModernBERT. So what is ModernBERT? Well, so as I already explained, Google released the BERT model in, I think, 2018. Yes, in October 2018. And so, as I said, at the time it got state-of-the-art results on benchmarks like GLUE, but also the SQUAD dataset, which is a question answering dataset, and so on. And after that, a lot of the attention went into GPT models, which are the decoder part of the transformer. So let's maybe recap a bit what the Attention is All You Need paper is about. So there they released basically a new neural network architecture called the transformer. And the transformer itself consists of two parts, an encoder and a decoder. So maybe let's go into the paper. Yeah, so the original transformer architecture proposed by Google includes an encoder part, which basically will take in some input, could be a text, and then it would encode that. So by encoding, we mean that basically the neural network, the transformer, would turn your text, your strings, into some kind of numerical representation, which is typically called a vector, also called embedding or encoding, which is not really human interpretable anymore, but it's like just a bunch of numbers that computers can use to understand language, for example. So if you would, for example, here forward a sentence as an input to the encoder of the transformer model, you would end up here with a vector representation, which is just a long list of numbers. And then you have the decoder part of the transformer. So the decoder part can basically be used to generate new outputs, for example, language, because that's what models like GPT-4, for example, are used for. They generate new text and they generate language. And so the original transformer model from Google was actually initially proposed for machine translation. So translating text from one language, for example, from French to another language like English. So in that case, you would forward first your French sentence through the encoder. The encoder part of the transformer would turn that into some kind of vector representation. And then the decoder part would take that vector representation, and as you can see, it's conditioned. So the decoder part is conditioned on that vector, on that encoding that the encoder has created. And then it would, what we call auto-regressively. So what we mean by that is basically one by one, one token at a time. It would then generate the translation of your French sentence in, for example, English. So that's what the decoder part can be used for. It can basically be used to decode that encoded representation of the encoder into some output, like for example text in another language. But so yeah, I think the most important part here to keep in mind is just that the transformer neural network architecture consists of an encoder part, which can be used to turn some input like language or vision or audio into some numerical representation called an encoding or embedding or vector representation. And then the decoder part, which can be used to basically generate some new modality like language or vision or video and so on. Okay, and so the BERT model, which was released by Google in 2018, only used the encoder part of the transformer, so only the left side. So BERT itself, could only be used to take, for example, some text as an input, and then it would turn it into some embedding. So it could not be used to generate any text. It could only be used to, for example, classify text or perform extractive question answering, which is taking a piece of context, taking a question, and then indicate where in that context the answer to the question can be found. So only extractive question answering, not generative. And so, yeah, if you wanted to classify a text with a BERT model, what you would do is first forward your text through the encoder part of BERT to get your vector representation of that text, also called embedding. And then you would add what is called a classifier on top of that. So a classifier is typically implemented as a linear layer. So in PyTorch, you can find this here, which is basically just a linear transformation. So it would take your vector representation of your text that the BERT encoder prepared, and then it would basically transform that vector representation into what we call logits. So maybe I can use Excalibur to better explain that. So if we have the BERT model and we have the sentence here, hello, my name is Niels. I'm gonna make that a bit bigger. So yeah, I'm not going to explain how BERT works in detail in this video. I have some other videos on that. I might create another one only on BERT itself, because I made one on the transformer, which includes both the encoder and the decoder part. So let's view BERT as kind of a black box right now, but it would just take in your text and it would turn that into a vector or embedding. So, and I'm just going to write some random numbers here, just to illustrate like how these vectors typically look like. This is just one example. Okay. So we call this an embedding, or a vector, which you might know from high school, for example. Well, yeah, actually BERT will create a vector for each individual word or token in the input sequence. But then there's actually a way to combine all of those vectors into a single one, which we typically call a pooling operation. So pooling simply means that we combine the vector representations of all the different words into a single embedding. And so for a base-sized BERT model, because yeah, if you search for BERT on Hugging Face, you will see that there are actually multiple variants. There's a base-sized variant, but there's also a large-sized variant. There's also a small variant, and so on. Yeah, the size of this vector depends on the size of BERT. So for a base-sized BERT, for that you would have 768 numbers for your vector. Like the vector itself would consist of 768 numbers. You can actually also see that if you go into the files and versions tab here and then check the configuration of this particular base-sized model, you will see that what is typically called the hidden size, so that's the embedding size basically, is 768 numbers. Okay, and so yeah, so that's what BERT does. It's the encoded part of the transformer. It takes in your text, turns that into a vector. So then if you wanted to use BERT for doing text classification, what you would do is then you would add your linear layer on top, also called a classification head. Like this. And basically this classification head would take in your vector representation and would turn it into a vector containing as many elements as there are classes that you want to classify. So for example, if I would say here this sentence, I really liked the movie, and you wanted to classify this sentence with BERT into whether the sentiment of this sentence is positive or negative, then yeah, the classification head would basically turn your vector containing 768 numbers into a vector containing only 2 numbers. So we call these the logits, also called unnormalized scores. So what we mean by that is basically, yeah, these are the scores that the BERT model gives to your sentence for each of the classes, but they are not normalized. So they are unnormalized. We mean that basically you cannot interpret them as like probabilities where they sum up to 1. So this is why we call them unnormalized scores. So here I would say here this vector has as many numbers as you have classes. So in our case we have 2, namely positive and negative. But this is just our use case. Like, yeah, for your domain, for example, for your use case, you might want to use BERT to classify between 30 different classes. Well, in that case, your classification head would turn your vector here of 768 numbers into a vector containing 30 numbers. And then we can actually turn it into probabilities. Using an operation called softmax. So if we wanted to apply softmax operation over here, we would turn it into some actual probability numbers. Like for example, let's say it gives this then as an output. I'm just again making up the numbers here to illustrate it. But then it would, for example, say here that BERT gives 97% chance or probability that the text is positive. And the 3% chance or probability that the text is negative. Assuming, of course, that the second number represents the positive class and the first number represents the negative class. But that's in a nutshell how BERT works. And so in the transformers library, if we would go into the documentation of BERT, which you can find here, you'll see that, yeah, there are actually several classes defined. So there's a BERT model class defined, but also a BERT for pre-training, BERT for masked language modeling, and so on, BERT for sequence classification. And so, yeah, here, the BERT model in the transformers library would be the BERT model that does not contain this classification head on top. So it will only take in your text and turn it into an embedding vector, which in the transformers library is also often called a hidden state. So you can actually see that if you go here into BERT model. Okay, for some reasons, okay, we're already here. So as you can see, it's the BERT model, the bare BERT model, outputting raw hidden states without any specific head on top. So this is why, yeah, BERT model will only take in your sentence and it will turn it into an embedding or vector representation called the hidden state, but it can be used to classify text because it will only encode your sentence basically. But then there is the BERT for sequence classification model, which, as you can see right here, is the BERT model transformer with a sequence classification head on top, a linear layer on top of the pooled output, for example, for glue tasks. So this is exactly what I was explaining here. So the BERT for sequence classification, that's how the class is called in the transformers library. That's basically the BERT model, but with this linear layer, this classification head on top, which allows you to train BERT for what is typically called sequence classification, because this is a sequence of words. It's quite a general name, but yeah, this is actually a text classification. Okay, so that's in a nutshell how BERT works, and that's like the what we call an encoder only transformer. So it's like only the encoder part of the transformer, rather than the, yeah, I'm still learning Excalibur, as you can see. It's only the encoder part of the transformer. It's not involving the GPT, the decoder part of the transformer. And so, like BERT itself, it came out in 2018, which is 6 years ago. And after that, there was like a lot of development and a lot of interest into the decoder part of transformers, which is the GPT suite of models like GPT-1, GPT-2, GPT-3, GPT 3.5, and so on. GPT-4 are all the decoder part or decoder only transformer models, which can be used to generate text. But so, yeah, a bit weirdly, the BERT model itself didn't see as many other new variants coming out, as was the case with GPT models. There was only, for example, Roberta. So yeah, these models oftentimes have very funny names. So Meta, they released Roberta soon after BERT, which had the same architecture, more or less, but I think it was pre-trained longer. So it was, yeah, just trained for a longer amount of time. And it resulted in a boost in performance. And then another notable model is the DBERT model from Microsoft, which also involved some architectural updates to the BERT model, which made it better at classification of text. But also this DBERT model, I think it's from 2020. So also that is like 20 years ago, 4 years ago. So yeah, there wasn't that much development after that regarding encoder-only transform models. And so this changes now with release version 4.48 of the transformers library with ModernBERT. So ModernBERT is basically a modern variant of the original BERT model, which includes all of the innovations that happened mainly on the decoder part of the transformer over the last few years, but now applied to an encoder-only transformer model. And so it includes a lot of tips and tricks that people figured out when training GPT kind of models. Because like the encoder part and the decoder part of transformer models, they share a lot of the architectural structure, which means that you can apply a lot of the innovations that happen on the decoder part as well on the encoder part. So I'm not sure I should go over like all the individual improvements, but I can maybe quickly go over them so you can find the model as well on the Hugging Face. As you can see, the model has 150 million parameters, which is very small compared to all these GPT kind of models, like for example GPT-4, which might have more than 1 trillion trainable parameters. But this ModernBERT model is quite small. So in terms of size, as you can see, it's around 600 megabytes, which allows you to easily deploy this, for example, on the cloud or on premise even. So let's quickly go into the documentation to see what the improvements are that ModernBERT provides. One is they added rotary positional embeddings to support sequences up to 8,192 tokens. So one of the things about transform models is that they typically don't work well on very long sequences, or you cannot easily train them on very long sequences. Why is that? It's because transformer models, as the paper attention is all you need reveals, it relies on a mechanism called attention. So inside this encoder part of the transformer, some computation happens called attention. And so by attention, I think the easiest to understand that is by visualizing an attention matrix. Basically, it allows the model to pay attention to certain parts of the input to predict the output. So, and this is actually also one of the reasons why BERT is such a good model. It's because basically, if you take your sentence, like in this case, he later went to report Malaysia for 1 year, you would basically compute a embedding or a vector representation for each individual words, and then you would let each of these words interact with each other using this attention mechanism. So by attention, we mean that each individual word could look at each of all the individual words as well. So we call this self-attention, because basically we have the same sequence 2 times. So we just plot it vertically and horizontally. And then every single word or token can look at both itself, but also on all the other tokens or words in the sequence. So this is what we call self-attention. And as you can see here, the darker a certain color, the more attention goes from one word to another word in the sequence. And this is what makes these models so powerful. For example, for coreference resolution, like if you have she or he in a sentence, but also a name, like let's say I have the sentence, Niels is working from Belgium, he is a machine learning engineer, then the word he would pay a lot of attention to the word Niels in that sequence. And so this way the model would basically know that, okay, he refers to Niels. So we call this coreference resolution. And this is what makes these models very powerful. So they will basically create contextual representations, vector representations, that depend on all the other, like it depends on the context. So the vector representation that the model will create for each of the individual words here depends on each of the individual words used in that sentence. And so so as I said earlier, like BERT will actually create a vector representation for each individual word here. So I really liked the movie, but yeah, using what we call a pooling operation, we can turn it into a single vector representation called an embedding or hidden state. Okay, and so the problem with this attention, like it's very powerful. It allows basically the model to have each of the individual words interact with each of the individual words, basically. And in this way, try to understand language better. But the problem is that this doesn't really scale well computationally and also in terms of memory. So basically, the more words you have in your input sequence, yeah, the bigger this matrix is going to get, the more computations you will have to do. And so the attention mechanism in a transformer, what we typically say is it scales quadratically in the input sequence. So I'm not sure there's like a nice... Yeah, this is maybe one that could illustrate it, but basically the amount of tokens or words that you have in your input sequence, you see that the attention mechanism blows up. Like in this case, the computation time is shown, like the amount of milliseconds that it takes to compute that embedding vector representation. It scales quadratically in the input sequence. So that's like a limitation of the attention mechanism. So this is why the original BERT authors decided to keep the amount of tokens limited to only 512 tokens. So here in the original BERT model, they limited this to only 512 tokens. Yeah, by token actually we mean it could be a word, but it could also be a part of a word. For that I would recommend the token visualizer, which is a very nice tool, or it's called the tokenizer playground, where you can enter some text. So let's enter my sentence here. I really liked the movie. You can see that in this case, yeah, each of the individual words corresponds to an individual token. So we have 5 tokens over here. But if I would say, I don't think, yeah, Niels, as you can see, is quite a unique term. So it would be tokenized into 2 separate tokens. And you can actually see different tokenizers over here. So that's quite a nice playground. Okay, but so yeah, due to this limitation of the fact that attention scales quadratically in the input sequence and the amount of tokens in your input, the BERT authors decided to only train BERT on sequences having at most 512 tokens. So this was like a big limitation, because of course, if you would want to feed a very long text to that BERT model, it's simply not possible. Or yeah, there were some clever techniques, but it was a bit painful. And this is what ModernBERT now solves. Well, they basically use what is called rotary positional embeddings, which allows the ModernBERT model to be used up till 8,192 tokens. Yeah, rotary positional embeddings is... yeah, there's actually a very nice blog post regarding what rotary positional embeddings are and how they work. I'm not going to go into the details of that, but basically this positional encoding is also some kind of embedding that we typically add to the embeddings of all of the individual words to make the model know, yeah, the position of each of the individual words. Because typically what we do when we feed the sentence as an input to the model, the first thing that would happen is we would apply what is called an embedding layer. That's like the first part of the... Okay, I'm gonna use maybe the same structure over here. That would be like the first part of your BERT model. So it would be like an embedding layer. So it would turn each of your individual words into some vector representation. Yeah, I would have to create some very small arrows here, but basically each of the individual words or tokens gets its own vector representation. So one for I, one for really. Maybe let's put them at the place where they are in the original sentence. One for liked, one for the, and one for movie. And so again, each of those vector representations would look like this, and so on. But so we do this like for each individual token, and so they have like different numbers, of course. So we're just gonna add some random numbers here and so on. So each of the individual words or tokens gets a vector representation or embedding. But like right now, the model simply doesn't know like the position of each of those words. So this is why we add what is called a position embedding to it. So yeah, we would typically, well, in the transformers library, this is all done in the embedding layer, but let's add here maybe position embeddings, also called encodings. We would basically add them to each of the individual vectors. So then again, like the input would be all the initial embeddings for each of the individual vectors, and then it would add a position embedding. And for that, there are multiple variants. One is what is called absolute position embeddings. So for that, we would simply store a vector representation. Let's call it absolute position embeddings. Which would simply store like position 0, position 1, position 2, and so on. It would store a vector, like the model would basically learn a vector. It's like a lookup table. So embeddings can really be seen as a lookup table. Again, like position 0 will have its own vector representation. And so on. But so each of the individual positions, the model would learn a vector representation for that. And so the absolute position embeddings variant would simply say, okay, this is here my vector for the word or token I. It's in the position 0, so I'm going to look up here the vector for that position, okay, and then I'm going to add it. So we would simply sum this vector with this vector, and then that would be the vector representation or embedding of that token I after the positional embedding layer. And we do the same here. So this is the word really, okay, it's in the second position. Well, if we start from 0, that's index 1. So we look up the vector here and we add it. That's how positional, well, absolute position embeddings work. This is like the most basic variant of position embeddings, and this is what was done in the original BERT paper. But then more sophisticated position embedding methods came out. And so rotary position embeddings is one other variant of that, also called a rope for short. It's quite more sophisticated. To be honest, I also don't really know the details of that. For that, I would recommend the paper that introduced it, called RowFormer, which actually also is part of the Transformers library. So RowFormer is just a BERT model, but with rotary position embeddings. And so this is adopted by the authors of ModernBERT as well. Also, I think because people seem to have the best performance with rotary position embeddings. So this is probably one of the reasons why they decided to adopt it. And so, yeah, this is supported up till 8,192 tokens. So you might wonder, okay, why can we now suddenly scale up till 8K tokens? Well, it has to do also with what is called flash attention. So flash attention is like a very efficient implementation of the attention mechanism, which allows us basically to also support models with longer sequences without sacrificing for the performance issues that we have. So I think right now flash attention latest version is version 3. It's basically just, as you can see, even you can go to sequences up till 16,000 tokens. And it's still very fast, very efficient. So thanks to that, ModernBERT can also scale up till 8,000 tokens because it's using flash attention behind the scenes. Unpadding, yeah, is also interesting. So unpadding basically means, if we go back here, so a problem you have with training these BERT models, typically you train neural networks not like on each individual sentence at a time. That would be very inefficient. We typically train them in what is called batches. So by batching, we mean that we would group together several sentences, and then we would train the BERT model on each batch, basically. So let's say, yeah, you're training BERT here for doing text classification. I would have another sentence here, let's say, for example, another sentence, this movie was really bad. I didn't like the plot, for example. Yeah, as you can see right here, yeah, you have an issue because this one has 5 words, but this has more. And if you want to forward these 2 sentences through the BERT model, yeah, you need some kind of way to make sure that each of the sequences have the same length, because otherwise you can't do matrix multiplications. So what is done in the original BERT paper is, yeah, they would basically pad it. So by padding, we mean that we would add here special tokens to make sure that we basically have the same length, that we basically ensure that they'll have, for example, 512 tokens. So yeah, this is called padding. So here we would also pad it up till like until we have a sequence length of 512 tokens. Maybe, yeah, let's add one more here. So, and let's add here and pad everything till that length. Okay, but the problem of that, or the inefficiency of that, is that you're then doing a lot of redundant computations. So if I go back to my attention matrix figure, you would basically also do computations on padding tokens, like between padding tokens. So if I would draw here my attention, so inside of this BERT encoder model, we have attention going on. So let's visualize one attention matrix. So if we have the sentence, I really liked this movie, then so with self-attention, we basically allow this sequence to interact with itself. And so then we have like these padding tokens, which are also part of the attention matrix, because yeah, we're padding them, and so on. Yeah, so the inefficiency here is that, like, with this original way of training BERT, we would compute an attention score here between the word I, between the words I and really, between the word I and liked, and so on. But we also do this between padding tokens. And this is quite inefficient because afterwards we actually throw that away. We don't really use the attention scores between padding tokens. And so this is something that ModernBERT also fixes. So this is called unpadding, to ensure no compute is wasted on padding tokens, speeding up processing time for batches with mixed length sequences. Yeah, again, there's a whole paper around like how to do that efficiently. It's from 2022. So this is yet another innovation. It's actually quite clever, but I'm not going to go into like the full details. I'm just going to like, this is the gist of it. So basically here, as you can see, the problem of training models on sequences of different lengths, like in this case we have 3 sequences, A, B, and C, and this one has 3 tokens, this one has 2, and this one has 1, so we have to pad them up till the max sequence length, like 512 tokens. What they do in this paper is they basically will unpad the sequence, so they will basically remove those padding tokens and just create a single sequence which contains all of the non-padding tokens, and then they have some batch offset. So say they basically keep track of like, okay, the first sequence, like the first token starts at index 0, but then the tokens of the second sequence start at index 3 and so on. So they keep track of that. And then, yeah, they basically see whether it's possible to forward that single sequence across each of the layers of BERT. So as you can see, we first have the embedding module, then we have the encoder, and then the pooler. So the pooler is the thing over here. So at the very end, so as I said before, like BERT will like give you a vector representation of each individual word, but we turn that into a single vector using the pooler, or yeah, let's also call it a pooling head. So they basically check whether it's possible to forward that single sequence through each of those layers. I think that's possible or feasible for the embedding module, but then for the encoder where attention is used, they have a variant of attention implemented called FMHA. So it's like fused multi-head attention. Again, I'm not going to go into the details, but basically this allows them to train the BERT model without basically losing all of the waste on that computation on padding tokens. So so this is also something that ModernBERT adopts. Then they also replaced the original multi-layer perceptron layers with some variant that actually was introduced by one of the people that invented the transformer, Noam Shazir, who works at Google. So basically so what's happening over here within this BERT encoder. So after we have let's call this the token embedding layer, then we have the position embedding layer, also called encodings. After that we basically have the transformer layers or blocks, and we typically we're gonna multiply that multiple times. Like we're gonna have them applied several times in a sequence. So for a base sized BERT model, we will apply that 12 times. So we would have 12 of those transformer layers or blocks. And inside each of the transformer layers, we have two things going on, namely attention and multi-layer perceptrons. So attention is going on there, but also a multi-layer perceptron is applied to the vector representations of each of the tokens. So MLP or multi-layer perceptron is like the most basic form you could say of a neural network. It's quite a simple variant. Again, I'm not going to go there into the details, but basically what you can remember from this presentation is that we basically apply this transformer layer 12 times in a row, and each of those transformer layers is going to update the token embeddings of each of the tokens we have here in our sequence through both an attention layer as well as multi-layer perceptron layer. And so there is just a more efficient multi-layer or better performing multi-layer perceptron that is also being adjusted for ModernBERT. Then another thing which is quite interesting is alternating attention. So by alternating attention, we basically mean that we won't do global attention every time. So by global attention, we would mean that each of the tokens would also attend to each of the other tokens in the sequence. So that's what we see over here as well. This is called global attention because he is attending to he, but also to later, went to, and so on. And each of the tokens is basically interacting with each of the other tokens, including itself. But that's of course also computationally quite heavy because you need to make sure that each single attention score is computed between each possible pair of tokens. So what people also came up with is called sliding window attention. So by sliding window attention, as you can see, we only compute the attention between tokens that are close to each other. So as you can see, we basically apply a window that slides over the sequence. And as you can see, for the first token in our sequence, we would, for example, only look at the token that comes after it, the token that comes after that one, and then after that one. So basically the 3 subsequent tokens, and we would only compute attention between those, but we disregard all the other tokens. So this is also called local attention, because you're only paying attention to like local tokens that are close to you, but not all the tokens. So this is called sliding window attention. So this basically allows us to ensure that we also save some computation. And so ModernBERT alternates sliding window attention or local attention with global attention layers. So as you can see, they apply a sliding window of 128 tokens. So each of those windows would consist of like looking 128 tokens after you basically, but not further than that. But so they do this in alternating sequence. So basically we will have some layers. Some of these transformer layers here will apply global attention, but then others will apply local attention, also called sliding window attention. Yep, so that's another improvement that wasn't done in the original BERT model, but has now been included in ModernBERT. So flash attention, yeah, it's just like a big speed up in terms of like the attention computations, and allows them also to scale it up till 8,000 tokens. Flash attention is also redesigned to keep in mind like the underlying hardware that is being used. So a lot of these models like BERT, also ModernBERT, they need to be run on GPU hardware. And typically, yeah, nowadays it's mostly NVIDIA GPUs. It can also be GPUs developed by AMD, for example. And flash attention really takes into account like how can we ensure that the attention computations are done in such a way that we really optimize the computation on our GPU. So it's really like a hardware aware design of the attention mechanism. But yeah, going into the details of flash attention would deserve its own video. Just know that it's really designed by keeping in mind that we are running these things on NVIDIA GPUs and ensuring that computations are done in the most efficient way for the hardware as possible. And yeah, this is actually another thing. So ModernBERT itself is also really designed by thinking about like the actual hardware that we're running these things on to ensure maximum efficiency. And so one interesting thing I read there is that, yeah, they basically also looked a bit into the number of hidden layers, because in the original BERT model, this is 12. So for a base size model, what we have is like 12 of these layers applied, one after the other. And then we use a hidden size of 768 numbers for each of the vectors. But in ModernBERT, I think they use some different numbers. We can actually see that over here if you go to the configuration. So the hidden size, okay, it's also 768 numbers, but the number of hidden layers is 22, so that's different. So it basically means that we will apply this transformer layer 22 times in a row rather than 12. I think they also explain that in their paper why they do that. So you can also always find the paper by checking the archive tag. And then yeah, you can easily find the linked models. So I think they probably somewhere explain why they have 22 layers. Don't really find it directly. Model design, yeah, here. So ModernBERT has 22 and 28 layers. Yeah, so they have a base size variant and a large size variant. So you'll also find a ModernBERT large on Hugging Face, which yeah also is larger in terms of size. It's 1.58 gigabytes, and so this one uses, yeah, sorry, I'm gonna have to close some tabs here. So let's go back into the ModernBERT paper. So yeah, they use 28 layers for the large size variant. And so yeah, they use a hidden size of 768. And yeah, the multi-layer perceptron is basically gonna expand that to 2304 numbers. And the large variant, yeah, uses a hidden size of 1000. So basically, yeah, if you go from a base-sized ModernBERT model where you use 768 numbers for each of the vector representations of your tokens, they use, for a large-sized BERT, they would use 1024 numbers. So in the transformers library, we typically call that the hidden size. Okay, so yeah, that's about it for ModernBERT. I see that it's already super popular on Hugging Face, having nearly 3 million downloads, and it's being just released, so that's quite crazy. So yeah, I would definitely recommend you to check it out. You can easily fine-tune it on your custom datasets. We do provide, as you can see, a lot of resources for that. So this is definitely a very nice addition in the latest version of the Transformers library. But that's not all. This is just one. As you can see, yeah, they also included 2 trillion tokens in the pre-training data. So that's also much more, I think, than what the original BERT model was pre-trained on. But there's more. Like, there's also Aria, which is a open multimodal native mixture of experts model. Yeah, so Aria is being developed by Cohere, I think. No, sorry. It's developed by Rhymes AI. So let's check out this company. They seem to also, yeah, release some very nice open source models, and their latest model is called Aria. And so it's a multi-model model. So you will find it if you go to the documentation of the Transformers library. You will now find it in the multi-model section. And so it's a multi-model model. So I think this one takes images and text as an input. As you can see here, you can feed it an image of, for example, the cats. Oh, sorry, I missed a letter. Of the Coco dataset. So this is the famous cats image that we often use in the Transformers library as well to test our models. And then you can, for example, ask the model what is the image, and then you can forward that through the model and it would generate some text. So yeah, this is quite nice. Let's quickly check how large the model is. So it has 25 billion parameters. So that's of course way bigger than the ModernBERT model that we just saw. So in terms of size, as you can see, the model is like split into smaller pieces called shards. So we basically, yeah, rather than having a single file containing all the weights of the model, we split that up into smaller pieces. But as you can see, yeah, every file is nearly 5 gigabytes. So it's quite large. So actually there is a handy formula if you wanted to know like the number of parameters of the model, like how big is that in terms of size. Let me maybe also quickly explain that. So for this Aria model, it has 25 billion parameters. So this, like the size of your model, it depends on the precision of the weights. So by precision, I think Wikipedia probably has a nice Wikipedia page about that. Computation maybe. Yeah. So it's basically the number of bits that we're gonna use to represent numbers. So what we have is called full precision, also called float 32. In that case, we would use 32 bits per parameter to store the value of each parameter. So 32 bits is also, if you know that 8 bits is a single byte, so this means that we use 4 bytes per parameter. But we also have what is called half precision, also called float 16, and there's now also another variant called bfloat 16. There we would use 16 bits, or in other words 2 bytes to store each parameter. And nowadays we also have lower precision methods, like for example 8 bits. In that case, yeah, we use 8 bits, or in other words, a single byte to store the value of each parameter, and we even now have 4 bits or even lower, like 2 bits and so on. In that case, we would use a half a byte per parameter. But this will actually determine how big in terms of gigabytes, because bytes, that's how we express the size of model. So this will basically determine how large the model is in terms of size. So if you have 25 billion parameters, and I think the default precision, you can actually see that on the hub. So the precision here is the tensor type is bfloat16 or floating point 16. So it basically means that we're in this scenario over here, the half precision. So we use 2 bytes per parameter. So that means that we have basically 25 times 2 billion bytes to store this model. In other words, 50 billion bytes, or in other words, 50 gigabytes. Because the giga is 10 to the 9th, which is 1 billion. So that means that this model, Aria, takes 50 gigabytes of GPU memory to load it for inference. So I'm not talking about training here. This is purely for inference, for generating new text with the model. So you require 50 gigabytes. But this is, of course, if you use half precision. Within the transformers library, we do provide a lot of tooling to go lower, like to go towards 8 bits and 4 bits. There's a very nice blog post on that on Hugging Face. Making LLMs even more accessible with bits and bytes, 4-bit quantization, and QLoRa. So by quantization, we basically mean that, like, going here from full precision to lower bits, we call that a process called quantization. So this is also explained in detail in the transformers library. Quantization techniques are basically clever algorithms to ensure that we can represent numbers in fewer amount of bits without losing too much of the performance, because typically, like, a naive approach of that would result in a high performance loss, because you're representing numbers with less bits. But there are some very clever techniques out there, some very clever what we call quantization algorithms. As you can see, we now support a huge range of them. Bits and bytes was one of the first quantization algorithms to basically allow us to shrink down the size of these models from full precision, 32 bits or 4 bytes per parameter, towards only 8 or 4 bits. And in this way, this basically allows us to run these models on cheaper hardware, on fewer GPUs. And so I think even in the latest release of the Transformers library, there was a new quantization method being added, which is the HIGGS quantization, which is yet another method. There are a lot of quantization methods being developed. But so this is to keep in mind that, so this Aria model is quite large. If you wanted to run it on a GPU, you need 50 gigabytes of GPU RAM. All right, I highly recommend to check it out. As you can see, it does quite well. Here they compare to the Pixtral model from Mistral, which is also a multimodel, so a vision language model, which also takes images and text as an input and produces text as an output. So in things like answering questions on documents, like PDF documents, for example, it does very well. As you can see, it scores 92.6% on that benchmark. Also answering questions regarding charts and so on. It can even apparently do video generation, so you can also use it on videos. It's quite nice, of course, to see this. By the way, you can actually filter models easily on the hub. So if you go here to the models tab, on the left there is like a task filter. And so to find models that take images and text as an input and produce text as an output, you can find them on the image text to text filter. As you can see, for example, Moon Dream 2 is currently one of the top trending vision language models. All right, so that's for Aria, and this was contributed by Amerik from Hugging Face. Next up is Timm wrapper. Okay, so Timm wrapper, this is also quite interesting. So you might know the Timm library. Timm is a very impressive library created by Ross Waitman. So Timm is actually short for PyTorch image models or Torch image models. So these are a lot of computer vision backbones, basically, neural networks, that are being implemented in PyTorch. And so this is a really nice library that allows you to basically get started with state-of-the-art vision backbones in a few lines of code. As you can see, it already has more than 32,000 GitHub stars. And now we actually, so Timm is now part of the Hugging Face ecosystem. So it basically gives you access to all of these state-of-the-art computer vision models and more, actually also optimizers and so on, data augmentation. But now we made sure that there's like a tight integration between the Timm library and the Hugging Face Transformers library. Because many people love the API of the Transformers library, they're very used to it. And we also have what is called the trainer class, which allows you to easily fine-tune these models on your own domain. And so now we actually have an integration which allows you to use all of those models in the Timm library, which you can all find on the hub as well. So if you go here to the Timm organization, you can see that there are now more than 1,500 models out there supported in Timm. You can find them here also filtered, for example, by number of downloads. And so now there's like a very easy way to use each of those models in the Transformers library thanks to this Timm wrapper integration. So as you can see right here, you can just load a Timm model, like in this case a ResNet 50, trained on the ImageNet 1K dataset, so it can classify images between 1,000 possible classes with the familiar API of the Transformers library. So in just a few lines of code, you can classify images now, and it's compatible with the trainer class. You can also now apply quantization, so you can apply making sure that you go to a lower amount of bits, basically reducing the memory requirements of your model and so on. So this is really nice. This was added thanks to Pavel and Amy. Next up, Pixtral Large. So Pixtral is a vision language model created by Mistral. So Mistral is this Paris-based startup. Well, now they might not be a startup anymore because they probably already have a lot of people. And Pixtral is a vision language model. As you can see, it has 12 billion parameters. It's being open sourced by Mistral, so it has an Apache 2.0 license, which means that anyone can use it for commercial purposes, which is really nice. And this is now also fully compatible with the Transformers library. So this is quite nice to see as well. So it's among the best open source vision language models out there. Next up is ColPali. So ColPali is a very new method for doing multimodal retrieval, basically. ColPali would probably deserve its own video. Let me maybe quickly explain how ColPali works, and in the meantime let me close many Hugging Faces over here. So ColPali, okay. So ColPali is actually a very nice method for basically retrieving relevant information in PDF documents. This is typically useful in what we call RAG pipelines, or retrieval augmented generation. I will definitely make a video around RAG. This is not what I meant. Retrieval augmented generation is basically a way to augment models like ChatGPT with a knowledge base to ensure that they produce more factual results, and that you can basically chat with your database, with your textual data. The problem is, if you want to efficiently retrieve information from a knowledge base, let's say you have a lot of PDF documents and you want to and you have a certain question regarding those documents, like you have a question, for example, what was the revenue in 2023? So a typical RAG pipeline would simply take all of your PDF documents, it would apply OCR on them, so it would basically extract all of the text from them, and then it would apply some document AI models like layout detection models and so on, Yeah, to basically try to detect all the tables, figures, titles, and so on from your documents. And then you would apply the regular RAG pipeline. So for that, again, I will have to create a separate video, but you would have to chunk up all of the text extracted from those documents into smaller pieces called chunks. And then each of those chunks get embedded. So again, embedding is an encoding. So we turn each of those chunks into a vector representation. And then at retrieval time, so when you have a certain question, like in this case, the question is what are VITs, you would also turn that question, your query, into a vector representation, a text embedding. And then, yeah, you basically would do a pairwise comparison to find the most relevant chunk. And then within that chunk, you hope to find the answer, and then you can provide that chunk to a large language model to present the answer in text. But yeah, this is like a quite sophisticated way, especially if you have like very visual documents, like in this case, where retrieval performance typically isn't that high. Like for example, retrieval can be expressed using this metric in the CG, which is a metric normalized discounted cumulative gain. It's a metric used in information retrieval. So as you can see, the performance isn't that high. Because you're losing a lot of visual information. Because you're basically just extracting all the text from it using OCR engines and so on, and then you're basically doing the text-only approach. Whereas ColPali is like multimodal, so it will just take a screenshot of your PDF document, and then you would use a vision LLM, so a vision language model, to turn the several sections of your screenshot into an embedding vector representation. We also call these sections patches. So we would basically, in this case, we have 4 patches for a screenshot. And so using a vision LLM, we would turn each of those 4 patches into a vector representation. And then at query time, like we also use our large language model to turn that query into vector representations. This is also different here. As you can see, it creates a vector representation for each of the individual tokens or words in the query. And then, we also apply some pairwise similarity score. So we basically take the embedding of the first patch, we compare it to the embedding of the first token. We take the embedding of the first patch, we compare it to the embedding of the second token, we compare it to the embedding of the third token, and then so we do this pairwise for each of the embeddings. And based on that, we also try to retrieve like the most relevant section within our PDF document. But in this case, we're using the visual information from those documents directly. And this then, like the ColPali authors claim that this results in a higher retrieval performance. So they claim to have, for example, an NDCG here of 81%. And so there's actually a very nice package on GitHub created by Answer AI, which allows you, it's called Bialdi, which allows you to get started with ColPali also very easily in a few lines of code. And now there are also newer variants like ColQN2 and so on. But basically, the gist of this is that ColPali is just a method to do multi-model retrieval in a better way by using the visual information of your documents rather than extracting all the text from it and then using a text-only approach. And so ColPali can now also be used very easily in the transformers library. So if you go into the documentation and you go into the multimodal section, you will now find ColPali there. So this is very nice because now it allows people to get started with ColPali in a few lines of code, as you can see right here. So this will definitely make it easier for people to get started with this state-of-the-art multimodal retrieval method. And I also highly recommend to check out the notebook by Merve. Merve works at Hugging Face, and she created a notebook where she uses ColPali combined with a vision language model called QN2, which is one of the better vision language models out there at the moment, to do multimodal RAG. So I would highly recommend to check that out if you want to check out the state-of-the-art approaches for doing multimodal retrieval and generation. Alright, so ColPali can now also be easily used in a few lines of code. Besides that, some newer large language models were also added, like Falcon3 and Bamba. Yeah, I'm not going to go into too much detail over there. Those are just better, as you can see, decoder only language models, so they only use the decoder part of the transformer architecture. Yeah, Bamba is based on Mamba. So yeah, there's actually a debate where people wonder like whether attention will still be all we need, because that was the name of the original paper, and actually 7 years later, attention is still the mechanism that is used in all of these state-of-the-art models. And the question is, will there ever be like a newer architecture that is going to be used in these neural networks? And so Mamba is like an exciting new work. It's basically based on state spaces. So this is all developed at Stanford University, I think. Oh, sorry, no, it's in Princeton University and Carnegie Mellon University. But yeah, state spaces, to be honest, they are mathematically quite complex to understand, which might also be one of the reasons why they haven't gained a lot of traction yet. There's actually a very nice introduction, as you can see right here, to these newer state space models, or SSMs, on the hub. So if you're interested in that, feel free to check out this blog post. But so yeah, this might be a contender for like actually taking over these purely attention-based transformer models. But so far, yeah, the transformer-based models that purely rely on attention are still more popular. But so models like Bamba are now being integrated into transformers, so it also allows you now to easily explore those newer variants of large language models. Okay, and then yeah, actually, you can see my name over here because those are actually two things that I added in this release. So I, of course, can explain a thing or two about those additions. So ViTPose is now also available in the Transformers library. So I'm quite excited about this one. ViTPose is actually a very minimal model for doing human pose estimation. So by human pose estimation, I think the best way to explain that is by finding an animation. So this is basically what I mean. It's basically estimating the pose. So by pose estimation, also called key point estimation, we will try to find the around 17 key points. So like, for example, the top right shoulder, the left shoulder, the left arm, right arm, neck, and so on, within images or video. And so far there hasn't been any pose estimation models available in the Transformers library, but that changes now because ViTPose is now available. The reason I integrated this one is, well, I didn't do it all myself. I also got some help from a person from South Korea. Is that it's like a very minimal design for doing pose estimation. It just uses a very simple vision transformer, and a vision transformer is actually very, very similar to this whole BERT model that I explained, except for like the input layer. But also vision transformers, they would require their own video to explain that in detail. But basically, and also yeah, they got like very good performance given their very simple design. So I thought it would be very nice to integrate it. And as you can see, they released also a huge amount of weights over here, both in base, but also large and huge and even giant variants. So I thought it would be nice if people can get easily started with the ViTPose model. And so now if you go into the vision models section, you will find ViTPose over there. And as you can see, you can now use it. So yeah, ViTPose is what we call a top-down pose estimation model. So what we mean by that is that it actually it depends on an object detector first. So if you have a certain image, you would first have to apply an object detection model to detect the individual persons, and then you can crop out those persons from that image and feed those to ViTPose. So that is called top-down pose estimation, because there's also another variant called bottom-up pose estimation, but so in the top-down approach, we first spot the person in the photo and then we try to estimate their pose. And so ViTPose is an example of that. I think the best demo there is to find there is this one by HIGGS, who also works at Hugging Face. He created a very nice demo to, as you can see, this is what comes out of the model. So as you can see, it first detects the persons using another object detection model, which we also integrated in the Transformers library called RTDETR, which is a very high-performing and Apache 2 licensed object detection model. And then, yeah, we crop out the persons from the image and then we feed that to ViTPose. So as you can see, well, the poses themselves are maybe not highlighted that much over here, but you can see that the pose estimates are done quite well, and you can actually also run it on a video. I think in that case it's being run frame by frame. And yeah, this thing over here, this space, which is kind of a demo on Hugging Face, uses 0 GPU. So 0 GPU is something very nice, something very clever. It basically, yeah, allows you to use GPUs for free on Hugging Face. Well, if you get a grant, or if you can also, of course, subscribe to Hugging Face Pro if you want to get easy access. But it basically makes sure that hundreds of GPUs are shared across all these spaces on the hub. So this one is also running on 0, and as you can see, you can now see also what are the top spaces, the most popular spaces that are at the moment using GPUs. And so this one is also running on 0 GPU. And so yeah, as you can see, the output is quite nice. So I'm very happy to see that ViTPose is now also available in the Transformers library. In a few lines of code, you can get started. And actually, I think we still are planning to convert some more models, because right now we only have converted the base-sized variants, but there are actually also small variants and large variants. So we definitely are going to add support for those as well. So ViTPose now available in the Transformers library. Then Dino V2 with registers is also available in the Transformers library. Dino V2 with registers, yeah, is from this very interesting paper from the Dino V2 author at Meta. Basically, Dino V2 is a very good computer vision model, especially for dense tasks, like for example, if you want to do segmentation in an image, or if you want to do depth estimation in an image. Dino V2 is a very good model for that. And it's actually very popular on the hub. So you can find Dino V2 as well in all kinds of sizes. So for example, the small variant, well, this is actually the registers variant. Let me find the large variant, for example. But so they noticed a interesting artifact in the original Dino V2 model, and not only in that one, also, for example, in this one, when visualizing the attention. So again, this is actually a attention matrix, because in computer vision applications, if we want to apply a transformer, we basically are also gonna turn our image into a sequence of tokens called patches. So these are just small sections, small pieces of the image. And so the model is gonna treat them as tokens, and then we can also do attention between tokens, so between image patches, basically. And as you can see, when they visualized the attention patterns, yeah, they noticed like some funny artifacts over here, as you can see, that don't seem to be related to the image. So they were wondering why that is. And they fixed that with this paper, where they added so-called register tokens. So as you can see now, those artifacts are gone, and it actually also resulted in better performance. So what turned out, what was happening is that the model was actually using some image patches as like computation tokens. So it was like trying to store a lot of information about the image, like global information, within those patches. But so those are typically patches that weren't that useful for the model. So rather than creating a vector representation for that individual patch, it was like using these tokens, these patches, to store like global information about the image. So this is like an artifact, and so they fixed that in this paper by adding some register tokens, or like tokens that can be used for like global computation to the model during pre-training, and then afterwards, yeah, you can throw them away. So after pre-training, you can throw those register tokens away. And this, yeah, resulted in like better performance. And so, yeah, Dyno V2 with registers has now been converted. So you can now use them on the hub. So if you search for Dyno V2 registers, I would recommend to use those now in favor of the original Dyno V2 models, because yeah, adding register tokens will always result in better performance. All right, and then, yeah, as you can see, the release is really packed. There are even more additions here. There is EMU3. So yeah, this one I don't really know in detail how it works. I just know the model is, I think, in terms of architecture, relatively simple, because as you can see, they say next token prediction is all you need. So this is also a multimodal model that basically converts any modality. It could be text, it could be images, it could be video, and then provides that sequence of tokens to a transformer decoder. So again, only the decoder part of the transformer. And then they train the model, they pre-train the model on predicting the next token, simply in the same way as you would do with the GPT model on text. But you can now also do this on video or on images, where it needs to predict the next frame, for example, or the next pixel. And I think, yeah, this model then can be used for all kinds of tasks. So it can be used. Oh yeah. So yeah, if you want to turn, for example, a video or an image into tokens. So one way could be as done in the Vision Transformer paper. So for that, let me go back to there's a very nice animation for that here. This is basically how the Vision Transformer turns your image into a sequence of tokens or patches. So it basically takes those patches and treats them as individual tokens. So this is one way to feed an image to a transform model. So you treat those patches as tokens. But another way is by using what is called a VQ-VAE. What do we mean by VQ-VAE? Actually, yeah, this is nicely explained here. This is invented by persons at DeepMind. Basically, you take your image and you train what is called an autoencoder. So you train one neural network to take your image and basically convert that into a sequence of discrete tokens or discrete numbers. And then you have a decoder which takes those discrete tokens, those integer numbers, and it will turn that back into the image. And so the goal here is that we basically create what is called a code book, or also a vocabulary of like these integer representations where the model learns an embedding or a vector for each of the numbers. So basically, again, this is like a lookup table where we say, okay, index number 1 has this vector, index 3 has this vector. So the model will basically learn an embedding or a vector for each of those numbers. So for a given number k, which is the codebook size of the vocabulary size. And then the goal is basically that, yeah, we have a model that can really nicely discretize images. So it can basically take your image and turn it into a sequence of integer numbers. And then using that decoder, you can turn that back into an image. And so then we can use these numbers as our tokens, and we feed those tokens to a transform model. And that's what is being done in this paper over here. So this is what they call tokenize and then de-tokenize. So by tokenization here, we mean that we would take our image or a video, we use a neural network to turn that into these discrete numbers, and then we would feed those discrete numbers as an input to our transformer decoder. And then at the end, we would need to de-tokenize them again. So then we would use our decoder part over here of our, yeah, so this whole architecture is called a VQ-VAE, a vector quantized variational autoencoder. But also that one would deserve its own video. But basically, yeah, the main thing I want you to know about this one is that it allows you to takes some continuous input like an image or a video, and it allows you to discretize it, to basically turn it into some discrete numbers. Because once we have discrete numbers, we can feed them as tokens to a transformer model. And then once the model predicts some other tokens, we can then again use our decoder to turn them back into some continuous representation like an image or a video. So this is what they use in this paper. And so this means that you can then use it for generating images, but you can also use it for generating text, generating video, and so on. So as you can see, it can do text to image. So given some text tokens, it can produce some image tokens, some discrete numbers, and then we can use our decoder part of the variational autoencoder to turn those back into an image. But it can probably also do more like interpolating between images and so on. So I would definitely recommend to check out this model. It's now also available, as you can see. They mentioned the VQ-VAE over here to tokenize your visual data. Then there's also a new model by Cohere. So Cohere is a large language model company based in Toronto, Canada. And they also added a new large language model called Cohere 2. So we can also find that one now on the hub. Oh yeah, I think it's only called Cohere 2 within the Transformers library, but maybe not necessarily like that on the hub. Oh yeah, it's for the Comment R7B model. So it's an open weights research release of a 7 billion parameter model. Okay, so yeah, as you can see, you can now also use this LLM, which has 7 billion trainable parameters in just a few lines of code. And this is the corresponding model that you can find on the hub. But be aware that this is only for research purposes. So as you can see, the license says that you can't use it for commercial purposes, unless I think you request a license from Cohere themselves. So be aware of that. All right, and then some other additions over here. TextNet, I was also involved in that one. The reason why we're integrating TextNet into the Transformers library is because this is part of a paper called FAST, which is a model that can do text detection. So as you can see, it can detect all the text in a video, for example. I think it would be very nice if we can support this one in the Transformers library. And it uses TextNet as a backbone. So a backbone is typically the first part of your bigger model. It's typically neural networks consist of various smaller modules. And so a backbone is typically a neural network that takes your image and turns that into a vector representation or embedding. And so this model called FAST uses TextNet as the backbone. So this is why we integrated TextNet into the Transformers library, because the next step is going to be integrating then FAST into the Transformers library as well, so that people can do text detection as well. So it's nice. It's a lightweight model, and it comes in 3 variants: a base-sized one, a small-sized one, and a tiny version. So it's really optimized for text detection. Then DiffLlama is also being added now. This one combines the llama architecture with the differential transformers attention. Okay, so this is, I think, a new attention variant. But yeah, I would have to read this paper into detail regarding, they say transformers tend to over-allocate attention to irrelevant context. In this work, we introduce the differential transformer, which amplifies attention to the relevant context while cancelling noise. Okay, so that's quite interesting. So as you can see, it seems to be a new attention mechanism, which is an alternative to the original one proposed in the transformer. But other than that, I think the architecture mainly stays the same. And they also claim to have better performance on several benchmarks. So yeah, if you're interested in checking out this newer variant of the attention mechanism used in transformers, be sure to check out this DiffLlama model. Yeah, Llama is of course the quite known large language model developed by Meta. Right now, Llama 3.3 is the latest version. Yeah, Pixtral, I already talked about that. Moonshine is yet another model that was also included in this release. It's an autoregressive speech recognition encoder-decoder model that improves upon Whisper. Okay, that's quite interesting. So yeah, Whisper is of course a very high-performing and very popular model on the hub for doing speech recognition. So
going along slushy country roads and speaking to damp audiences.
If you have this audio, this is what comes out of the model. So it's a speech to text model. And so now apparently there is a new model called Moonshine, which was integrated. So let's check that out as well. So that's quite interesting. So yeah, for speech recognition, transformer models are also very powerful. Again, there, the architecture is very similar. Again, we will use the attention mechanism. The only thing that is different is the way we feed the modality, in this case audio, to the model. But for that, I would recommend to check out the Whisper paper, where they explain how they feed the audio into a transformer model. But other than that, as you can see, it's always an alternating, it's always a bunch of these transformer encoder blocks, each block consisting of a self-attention layer and a multi-layer perceptron layer. So it's nice to see that there are some new models out there for speech recognition now also available. So you will find these in the audio section of the transformers library. So if you go here to audio models, you will hopefully find Moonshine over here. So yeah, you can now also use that in a few lines of code. And then yeah, I talked about quantization. So as you can see, two new quantization methods were added in this release, the HIGGS one and the VPTQ one. I would recommend to check out the papers if you want to know the details regarding how these quantization algorithms work. But so they are quite easy to use. So the way you can use quantization methods in the transformers library is by providing one of these quantization configs to the from pre-trained method. But yeah, there's a whole guide on that. And also, yeah, it depends also on the hardware where you want to run these quantization methods on. Not all quantization methods support all the different hardware providers. All right, I think that's about it. That's all the things that were included in this release version 4.48 of the transformers library. So as you can see, it's really packed. I hope this overview was helpful for you. Yeah, to learn a bit about all the things the Hugging Face team is working on, making sure that the latest and greatest AI models are being made accessible to people. And yeah, of course, I'm looking forward to the next release. We will definitely have a lot of new exciting models coming out in the next few months as well. So yeah, I hope to create several of these videos in the next few releases as well. So hope to see you there. Bye bye.